think it should go now. All right, we got it. Copy video URL. God damn. Actually posted it. Post. There must be something way better. Jesus Christ. The formatting is garbage. Forgot to select the build in public thing. Okay, let me save this one. Okay. Okay, so guys, sorry for taking so long on this. And today we're going to continue where we left off yesterday, which was studying a little bit how the LEB128 work. I had an initial impression, but it actually changed completely. Because I still don't know what is actually storing into the... Remember that I almost crashed this thing, right? And then I ended up having to open Firefox. I'm gonna come here to VS Code. I'm gonna come and I added all these console logs because I wanted to understand what was actually storing. The question that I do have, that I was asking myself, let me ask it. In the code above, I want to know if the console logs are printing integer numbers or if it's possible for me to print the binary representation. Okay, so that means that I gotta go and do this toString 2, toString 2, and then I'm just gonna copy this. Gonna come back to the browser. Clear. Gonna paste this. And I'll say LB128 2. Right. So what it actually does is that it does store the entire integer, and let's say lab 128, 129. You know what? That's the thing that I do not understand. So theoretically, if it's like unsigned, then if I say 6, yeah, I understand it now. I got this. Okay, so it's actually storing the integers. Include console.log val before bit val to string 2. I'm gonna add it here. So the value is going to be, then we add the 7-bit mask, which is the and, in which it'll try to extract, right? The 7 for the first 7 matching 7 bits. I think I should definitely do something like this. Fill or JS bin. And I'm gonna add this HTML, JavaScript, adios. And then I'm just gonna say lab 128. Maybe 128 2, for example. I say run with JS. All right, I forgot to copy my constants. I wonder why it's not showing up in the console. Oh, because it's the output. It's not the console. Run. Okay, value before bit. This equals 10, of course. 0 and 1, then B. 0, 10, 1, 0. So what's actually happening is that if we go to the bitwise AND operator, it will only match those that have like 1 in them, which basically means that, remove this, and the bitwise OR operator, binary has a 1, it will actually get myself a 1. So what's happening in the first one is that we are extracting only those first characters that have 1 into them. Let me see something. No. In here, what we're doing is that we're extracting up to the 7-bit precision. That's what's happening. So it will always do the pair of 256. I do have a question. What happens if I, for example, say 128 and then I run it? Does this run like for infinite? Yeah, it doesn't take into consideration the, yeah, I crashed the page. Wait, I crashed it. So, that's pretty nice. So this only takes into consideration the positive numbers, right? And what I'm understanding now is that what this is doing is that the LEV128 so far, what's actually doing is that we use the 7-bit mask to always encode, or no, always extract the pairing of 256, because what we're planning practically doing is 2 to the 7. Let's see if this actually works. 128, so 2 to the 8. It's actually doing this. I say, for example, that I say 250, no, 128. Then I run it. About the 4-bit, right? This is the entire thing. That's 0, right? So B0 val after bit. So what it actually does is it removes, right? It shifts. The shift operator. So if I keep shifting, it will extract, and val after bit, it will receive only 1. B continuation bit. So it says continuation, which is a symbol 1 because it's only 1 bit. But if I say, for example, 129, I want to clear this. What I do not get is const r console.r is why is this stored? What I do not get is why this gets 129 and 130 the same. If I actually say 255, it should count me 2 right now, right? Okay, still 1. 256 counts me 2. Because I'm pushing our value, our val. We remove the first 7. Should be 9 positions, right? 1, 2, 3, 4, 5, 6, 7, 8. 8, 2, 3, 4, 5, 6, 7, 8, and 9. Exactly. Because we're jumping in terms of 128. 128 to 56. If I put 512, it should be 10 positions. And I'm gonna do this b to string to length clear. Clear, run. Here you go, 10. Oh, it's actually doing it in separate rows. So, right, 10. This is interesting. Why do I get 128 and then I get 4? Is it because it's restarting? I think that I should answer myself just by continuing. 8 bits, 8 bits, 14 bits. Let us reread this. Assign argument to be developed since 7 bits. Okay, anyways. Create a constant that holds a continuation bit mask. Initialize a flag called more to know if we should keep decoding. Let's start with some boundary numbers. Big unsigned integer to lib128 to make it work better. Well, starting tomorrow, I think I'm gonna do 2 days of or 3 days of developing and 2 days of actually checking the WebAssembly. This book, because I know that we're heading like very deep into things that aren't necessarily like the best thing we can actually do. It's actually pretty interesting. I'm skimming through the entire page to see if there's anything testing unsigned LEB128. The LEB128 encoder. So the question that I still have is, we're still in here, right? And the question that I still have, because remember that I know very little about the continuation bit. I think I have this in Firefox already signed in. And boop. I want you to explain me with a lot of detail on what happens with this algorithm. I'm trying to re-implement the LEB128 WebAssembly algorithm, and I do not understand what are we storing inside the arrays. Array R. Glow with Claude Sonnet. Little Indian base 128. Encodes integers into a variable number of bytes. Each byte stores 7 bits of the actual number. And uses the 8th bit, the most significant bit, as a continuation flag to indicate whether more bytes follow. Constant. This is the flag bit. Mask the lower 7 bits. Storing an array R. The array stores the encoded bytes of your number. Each element is a byte. The encoded bytes of your number. Each element is a byte, 0 to 255, that represents either a chunk of 7 bits from your original number or a chunk of 7 bits from your original number plus the continuation bit, if more bytes follow. 624, binary 10001, iteration 1, vol. 64, binary 1, and so the lower 7 bits equals 48, right? Because we're actually shifting this to the 7th thing. 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. Which would be 0, 11, right? 1, 2, 3, 4, 5, 6, and 7. 7, 0, and 7. Only these two match. So only these two match, and we extract the lowest 7 bits. Wow. We shift right 7 bits. Which would means equals 4. I think that the problem is that I'm having difficulties understanding how shifting and all of those things work. That's the thing. I need a better explanation how shifting works. And why do we use them in here? Yeah, that we understand from documentation. 179, 127, 7-bit mask. I love this explanation. Okay, 1, 1, 0, 0, 1, 1, 51. Yeah, but you kind of messed up in here. You said it was like 48. One 12. One, 2, 3, 4, 5, 6, 7. Right. So you got this wrong, baby. Oh no, he has another example. He says 179. Okay, that one was correct. 51 truth table. 0 and 0, 0, 0 and 1, 0. 1 and 0, 0. 1 and 1. Only this produces 1. Okay. 0 to 6 survive. But 7 plus becomes 0. the right shift, the divide by powers of 2 operator, what it does, moves all bits and positions to the right. Bits that fall off the right edge are lost. Oh. So it says move it to the 3, so that means that I am going to move this 3 to the right and just gonna get the 0, 1, 1, 0, 1. So we fall off the edge. It's like dividing by 2. Damn, this is so interesting. Divide by 128, which is the encoding. LEB128. After extracting the lowest 7 bits, we discard them by shifting right 7 positions to be extracted in the next iteration. Okay, the combine operator, what it does, compare bits and produce a 1 if either bit is 1. Why are we using LEB128? This sets the highest bit to 1, the continuation flag, while preserving the lower 7 bits of data. So that's why we got 1 0 0 0 0 0. Right. Wait, give me a second. 10 bits. Extract the lowest 7 bits. We get 48. Okay, shift right by 7. And then you get 4. 1, 2, 3, 4, 5, 6, and 7. 2. But that's not 4. That doesn't look like 4. Bytes bit to number. Binary to decimal converter. Binary number, convert. 4. Why? 0. Oh, right. My bad. We're starting 0. Of course it's 4. This is 1. Well, this will be 5. Right. Yeah, my bad. My bad. This is 4. Good. Good. My bad. I got it. My bad. It's actually 49. Yeah. Okay. Because it's a 0 based. In continuation bit. R push V continuation bit 128. It's actually 176. So I think no continuation bit. False 0 loop ends into 7-bit pieces, labeling each piece except the last one. I think everything will make sense to me if I can see a decoder. What would be a decoder to this algorithm? Here's the LEB128 decoder. So here it is. It's a for loop. I minus bytes dot length. But one thing. So you're passing in the array, right? Okay, let's go to 178.5.64 back to 64. Iteration 1 byte. So that's why I wasn't able to read it properly, because I wasn't understanding what was going on. Like, we're gonna read it in bytes. We need to read it in binary. It's like a complete mind shift that I gotta do, because if I keep doing this, then it won't work out. So I got the byte equals 176, data bits equals byte and 7-bit mask. We got the 176 and percent 0, 127. Then we got data bits 48. Add the result to position 0. We start 0. And then we add this. Wait. Break down to me what's happening in this line. This line does two things. Shift the data bits to left to the correct position. Combine them with the existing results. Let me show you how. Shift the data bits. 48 left by 0 positions. Shifting means by 0 means don't move. Step 2, OR with result. Our empty result, right? 0, 0, shifted 48 data bits. So we gotta do that. We gotta start somewhere. But why do we even have oh, it was actually breaking in at position 0. Right. Okay, I get it. I get it. 0 and shifted, and the shift, which is still. I thought that the shift was going to remain constant. Byte and 7-bit mask. Because aren't you like moving into the ledger, to the ledger, or like the cliff? Okay, so we got here 048, right? 48, it returns 48, right? Which is the first byte. Check continuation bit. Okay. Byte and continuation bit different from 0. This has more, which is move to the next 7-bit position. Okay, so here we are increasing the shift. We're not doing anything. Byte and continuation bit needs to be different from 0. If we go back in here, what's going to happen is that anything that matches this is going to have a continuation bit. .176 through 128 is not 0, so has more equals true. Iteration 2, byte equals 4. Binary. Extract data bits. 4, 127. It's only going to be this one over here, right? 4. Add result at position 7. 4, 7 means shift 4 left by 7 positions. It's going to be, right, this is going to be 4. And, well, this is 4. Now we're gonna move it 4 positions, 7 positions. 1, 2, 3, 4, 5, 12. Now combine with result. Does this make it click? Shift the data between the last two representation, combine them with the existing result. Iteration 1. Shifting by 0 means don't move. Exactly. I understand that. No, I begin understanding. Or with the result. Shift the data bits. Shift 4 left by 7 position. Watch. Before the shift. Add 7 zeros to the right. Right. I do have a question. Why? If the shifts are in increments of 7, why do we keep adding on the 7? Like 7, 14, 21, 28. Wouldn't the shift by itself work? By 7 work? I don't know if I made the right question. In encoding, we need to track shift. When encoding with it, we are destroying the original value, so we go, right? We just throw away the lower 7 bits. Throw away 7 more, until you got 0, right? I understand that, because we're always working on whatever bits are left. Decoding, we must track cumulative shift. Because the thing is that if we're okay, let's say we are encoding let's say 800, and this is our binary. And this is our number, right? And what we're doing is that we're shifting 7 bits, 2, 3, 4, 6, and 7. We're always extracting this. Well, I think it should be something way bigger. Let's say 8,000. 13 digits. 13 digits? No. Something even bigger. 80,000. 17 digits. Okay. One, 2, 3, 4, 5, 6, and 7. We got in here. We got this one. We're gonna have a blue color. I'm gonna duplicate now. Is it like this? Or is it like this? So from my understanding, like this is reserved for a flag to see if you actually continue or not. Yeah, these are the trick of binary. So it should be like in 3, right? But the question is that I have, like you have then, oh man, my baby just woke up. Guys, I'm sorry, I'll have to drop out the stream. I gotta take care of the baby. I think that we're gonna continue this next week. Because next time I'm just gonna focus on the Crunchyroll subs. So thank you very much for listening and tuning in. We'll be back.